And so we'll continue with a talk that is really original. This is why we selected it to be one of the opening talks about nuclear rust by John Darrington. So hello, John, how are you?
Good morning. How are you?
Doing well, doing well. Really glad to have you here. Just to let you know, as a apidays, as a conference, we organize the Digital Sustainable Challenge. You know, it's every year for 3 months. We ask the community to refactor their application or design according to eco-design principles. You know, architecture and stuff.
Mm-hmm.
And also, we received the Shift project, the Green Software Foundation. So we really try to make our community aware of what's going on a green software, but like now it's in your proposal, we really love the fact that you say, okay, but like how software can help, you know, like energy or production or energy sources or whatever to be developed with digital twins. And this, we're really interested by what you have for us.
Well,
So the stage is yours for 25 minutes, and we look forward to it.
Awesome. Thank you very much. Okay, well, hi there. I'm John Darrington. I'm the lead architect for digital engineering at the Idaho National Laboratory. I'm extremely excited to speak to you today. I constantly feel like I'm doing some of the most interesting work of my career right now. Hold on one sec. There we go. And it's a different beast presenting online, especially to such a large and diverse audience. I constantly, I worry a little bit. I don't get stage fright because I can't see faces, but I think there are some special challenges when it comes to keeping your attention. It's so easy for you to minimize your window and browse Reddit, enjoy that while it lasts. But stick with me though. I tried to find something practical, and I tried to find a title as catchy and as interesting as the stuff that we are doing at the lab. So just a quick blurb about me. I've been working with the Idaho National Lab for the last 4 years in their Department of Digital Engineering. We do a lot with data management, digital twins. Prior to that, I was working in the commercial area. I did a lot of international e-commerce data management work, international e-commerce transaction work, all of that jazz, and have been in the data management and API world for quite a long time. I also helped develop for the Idaho National Lab an open source data lake called Deep Links and various tools in that ecosystem. So let's go ahead and get started. Let's look at this picture here. Now the scale of this photo might be hard to see at first, but off to the left you can see this red line, and it's part of a crane truck. At the very bottom of that red line, you can see a little truck with its support arms. If you watched the news at all during a period in 2011, you might have an idea of what this is. It's one of the damaged buildings of the Fukushima Daiichi nuclear power plant in Japan. Now, the Fukushima incident in Japan came about, let's skip that, because a 15-meter high tsunami disabled the power supply and cooling of 3 of the Fukushima Daiichi reactors. And 3 of those cores largely melted in the first few days of the incident. And it took until December of that year, so later that year, to reach a cold shutdown condition into where they were able to get into the reactor and do the things they needed to do. And this was a big nuclear disaster. Thankfully, death counts stayed low to non-existent, with most deaths being attributed to the earthquake and tsunami rather than the nuclear disaster. So thankfully, it could have been a whole lot worse. But why do I bring this up? And I think it has to do with this, is that no industry is immune from accidents, but all industries learn from them. The Idaho National Laboratory has had a large part in nuclear history in the United States. It was at the heart of the first city run on nuclear energy in the States, Arco, Idaho, and has helped researchers learn how nuclear material behaves and misbehaves. So nuclear energy has basically had 3 large-scale disasters: Fukushima, 3 Mile Island, and of course, Chernobyl. From each, the nuclear industry has grown more and more adept at managing and monitoring the risks related to nuclear energy. It's not all roses, though. A safety focus while extremely necessary and good in the nuclear world, has had some adverse effects on the software development industry, which supports it. So let's talk a little bit about the nuclear software industry state as I've seen it and as I've dealt with it in the last little bit. First, it's very risk adverse. When you're dealing with nuclear energy and you're dealing with nuclear materials, you are very risk adverse because you do not want to cause any incidents. You don't want to introduce new and unstable technologies. You want to avoid that. And because they're risk adverse, change is slow in the industry. And being able to create new technologies, new APIs, new software, and have those launched into the nuclear space can take a long time. For example, there's something called NQA1 certification for software, and it is very many pages long of regulations and rules that your software must follow, how it's designed, how it's built, how it's developed. And so it makes it very slow and very difficult to build new tech in the nuclear control industry. Everything feels like it's done in committees. And now this can be a good thing, but in a lot of cases, it does slow things down. You get a lot of politics involved with software and technology choices when it should be something that's looking more at the tech and what can work instead of something along those lines. And so things being done in committees leads to a set way of doing things this way because that's the way we've always done them in the industry. And I see that far more in the nuclear industry than I have in any previous industry that I've worked in, to where we do things one way and we stick with it and don't change it. And then the last, which is not an insurmountable obstacle, but is very difficult, is dealing with ancient protocols. I mean, we're dealing with very old code, very, very old APIs, ancient networking protocols, old binary file formats. And so when you're dealing with these things, a lot of the new tooling doesn't have software packages designed to create it. For example, LabVIEW's TDMS file format does not have reader libraries in very many languages, especially modern languages. And so it can be very difficult to read something in that file format. In fact, I've written a few to help out with that. So we're dealing with this. So this is where we find ourselves at INL, attempting to modernize the nuclear control and monitoring world with current tech and best practices while fighting decades of safeguards, some of which are either no longer relevant or were never more than a reactionary effort. Now, the next slide here, this is an original slide. So this is where we found ourselves. And so we decided that we needed to introduce a new technology into our work. And this is the original slide from a 2022 meeting. Don't pay too much attention to the word deep links here. We'll briefly touch on that a little bit later. But what I wanted to highlight here is that this original slide in 2022 is laying out the reasons why we decided that we needed to introduce new technology into the nuclear world and into what we were doing. So first of all, we were dealing a lot with Node.js, with a lot of our web-based services. But again, there's a lack of well-adopted scientific computing, at least at the lab. There's runtime requirements, so not really good for a low-level language. Python, again, has a runtime requirement. You can work with Python, but again, performance becomes a concern when it's not covered by the internal C libraries. It's permissive and allows for easy introductions to bugs. But my favorite bullet point off of this slide, and the one I kind of made a real push for, was the fact that we needed to make a conscious decision before the decision is made for us by accident. When designing your software or designing your APIs, conscious decisions before you're forced to adopt either a paradigm for accessing or a paradigm for displaying your data or anything like that is extremely important, because you want to control the things that you do, because the more control you have, the more powerful your software can become. And then the last bullet point here, which is safety and lower level languages necessary for operational control. Now, you might be asking yourselves, well, why do we need a low-level language, and why do we need operational control? What are we doing as a department that we need this kind of thing? And what we're doing as a department is building what you call a digital twin. Now, the digital twin levels, now these aren't comprehensive levels. This is just kind of a description. But I want to illustrate the fact that we move from this idea that a digital twin is just a model and some data connected to that model, so that the data and documents are kind of floating around, and they're connected to maybe a model or something along those lines. And we eventually connect all that data, up through levels 3 and 4. But the culmination of digital twin work, or at least the culmination of an actual digital twin, is having a model that streams live data into it, that has predictive analytics on top of it, and then has a feedback loop into an operations control, so that the digital representation of this physical asset can interact with the physical asset that it's twinning, and be able to run changes, to be able to change settings, to do whatever you would have on there. And the culmination of digital twin work at the department is the eventual autonomous operation of a nuclear reactor, with controls and operations partially dictated by live and predictive analytics. This is a huge deal, and it was a perfect test bed for moving forward with our new technology, our new API paradigms, and and just moving forward with this idea of the fact that we needed to change. Introduction of any new technology at a workplace is difficult. Introduction of brand new technology, at least by nuclear standards, into the control and monitoring systems of nuclear reactors can feel insurmountable. And we decided that if we were to express how these changes would serve us best, we would have to focus on the safety that such a change would offer us. Again, a stress on safety because of the nuclear engineering world. If we could convince them that this is a more safe move than continuing on with our current paradigm, then we move somewhere. So we decided to scare people a little bit first, do a little bit of a carrot and a stick, so to speak. Our stick was memory safety and why safety matters. And so I'm not going to read all these bullet points. I think you're capable of reading these, or at least looking at it after the presentation. But when you're dealing with low-level hardware and monitoring systems, segmentation faults can mean the difference between disaster and safety, or between an experiment being scrapped, being decided that it's not useful, and then being successful. So we tried to drive home the idea that current software and current programming paradigms all suffer from a lot of memory safety issues, and they can lead to security vulnerabilities, especially. And when you're dealing with classified data, or you're in that realm in the Department of Energy or the Department of Defense, you do not want security vulnerabilities. You do not want memory safety issues. And so again, it became a little bit of a carrot and a stick to help them understand that, hey, we have something here that can help you. And so once our focus became safety, the options available to us as technology became a lot more understandable. And we settled pretty quickly on one technology in particular. And you might know where this is going if you've dealt with this language before. This slide is, again, an original slide from that 2022 meeting. we were comparing different languages and technologies. We were comparing things like C++, Go, and then Rust. And Rust kind of stuck with us quite a bit. Again, it's sponsored by Mozilla, and some of this is inaccurate. And I wanted to maintain the inaccuracies so that we could maintain this original slide exactly how it was, so that you could see, into companies as they make decisions to shift technologies, what some of the presentations they might give are. But it's a statically typed compiled language. We can target all these different chipsets and OSs. You can actually run it without an OS. All you need is a memory allocator. There's no garbage collector. But what we focused on was the fact that concurrency is built in with an emphasis on memory safety in those concurrent operations. And that's exactly what we needed when dealing with nuclear reactors and digital twins. When we designed digital twins to bring in this data, when we designed these digital twins to interact with predictive and powerful analytics, we needed something that was able to be safe and concurrent. And again, this is not entirely accurate, and I think the community has grown at this point, but it kind of sealed the deal for us. And then what finalized it was this idea that we could interopt with other languages, because we're coming into the nuclear industry where we have to deal with various existing programming languages. We have to deal with C++, we have to deal with Fortran, we have to deal with a lot of Python code in our machine learning. And this idea that Rust could be interopted so that we could replace only pieces and bits and pieces of it meant a lot to us. And if you're ever familiar with something like the Strangler pattern, this idea that you slowly move things over into a new technology, well, Rust allows us to do that. And it allowed us to do that with existing technology. So within 3 months, we have a piece of software at INL called DeepLinks. It's an open source ontological graph data lake with tabular and time series data support. I'm not going to spend tons of time on this, but it was originally mostly Node.js. And I think you can already see some of the problems floating up with dealing with data with Node.js, because it's a single-threaded language. It does not have good compute power, because you're blocking their event loop, so to speak, when you're doing high compute. And so we introduced Rust into it 3 months after our initial discussions, by building a loader for taking tabular data and loading it into Postgres concurrently and more quickly. And we got up to loading something like a 100 or 1 million row CSV with 15 columns of 64-bit numbers in something like 1.3 seconds. And so we were doing very good with loading this onto a single node, and Rust allowed us to do that. Rust also drove our time series and tabular data model and our Delta Lake integration. If you're not familiar with the Delta Lake technology, I highly recommend it for data integration and data warehouses. And then we've been working with Redis Graph to load our custom graph schema in DeepLinks into Redis Graph so that we could use things like Cypher and a better querying layer than what we currently have. And then, of course, I don't think any presentation nowadays is complete without at least mentioning large language models. We are working with Llama RS, which is a Rust rewrite of the Llama C++ library for large language model solving. And we are looking at integrating that into DeepLinks. And so we've done a lot with Rust. And we've done more than just DeepLinks in Rust too. We have we have more than these two, but there's 2 other programs we have. One is called Serval. So another big cat. So we go back to DeepLinks is a big cat, and then Serval is another big cat. And what Serval is it's a WebSocket multiplayer game server, drives our AR and VR multiplayer integration. So for digital twins, we have a visualization layer that's usually in augmented reality or virtual reality so that users can interact with our virtual twins. And then again, it drives another part of deep links. We also made a loader that was a Python and C# module written in Rust for caching time series and tabular data. It leverages DuckDB, another technology that if you're not familiar with, I highly recommend that you check out. And then it's utilized in many of our machine learning and AI pipelines at INL. Finally, after a year of experimentation with Rust, with these new APIs, we were ready for the big time. This is the AGN-201 nuclear reactor. This is a fission nuclear reactor, and this model is rated for producing up to 5 watts of electricity. This particular model is located at the Idaho State University in Pocatello, Idaho, and is in active use. Not only do they have an active nuclear reactor, but that department also, I believe, has the ability to make their own fuel for the reactor. The NNSA and the Department of Energy asked Idaho National Laboratory to create and manage the first digital twin of a fissile nuclear reactor with this reactor as the target of the project. And this became a perfect test bed for our new technology and our new paradigms of working with this. So I wish I had more time to dive into deep links and our tech behind it. But what I wanted to show was that know that it, along with various other pieces of our Rust power technology, works in harmony to provide a cohesive digital twin of the AGN-201. Off in the right-hand corner, we had to push live analytic data from the data acquisition system of the reactor, some of this using 20 to 40-year-old technology, into the cloud. And once there, we had to organize and process it, bringing it into modern formats and setting it up for ingestion into various machine learning algorithms. And this was all done via Rust. We created a file watcher system on this particular system to deal with the file format. It pushes it into our deep links data warehouse, which then processes it and formats it and changes it into the right kinds of data. Now, while we are currently working on a comprehensive machine learning suite for nuclear engineering in Rust, we're actually rewriting an R library that we have created. We're not quite there yet, so we had to interopt with our Rust-based services and Python. And in order to maintain the speed, that's what we decided to do. We decided to write native Rust Python modules for this artificial intelligence and machine learning portion, that deep links loader that I mentioned earlier on, to work with this artificial and machine learning in that lower left-hand corner. And so once the data flows into deep links, it flows out into the machine learning algorithms, and we make predictive, we predict things on it. We have a neutronics model. We can make predictions on how reaction's going to be, all sorts of different things that are very important for nuclear reactor operation. Now, up in the upper right-hand corner, this live model and human interaction is kind of the window into the digital twin. We used the same Rust code that we took and created a C# visualization, so in Unity, which drives our augmented reality and virtual reality. And by doing so, by just continually sticking with Rust, we were able to maintain speed and accuracy without having to move to socket-based communication or having to redo our software in each language for each of these disparate systems. And so we were able to maintain these things by using that. Now, our bet paid off. We successfully launched the AGN-201 digital twin in less than 6 months. Now, part of that is because the deep links data lake already existed. However, the technology we used to push to the data lake and pull from the data lake could easily be adapted to any of those existing data lakes that currently exist in the cloud or off speed. We were able to maintain speed and accuracy of data by using native modules and Rust. But the most important thing that we did, and what we what I want to stress here is that we demonstrated the ability for Rust and current best software practices to eventually become part of current nuclear control instrumentation and paradigms. We were able to successfully demonstrate that, hey, what we do works. It's safe, it's powerful, and it gives you a solid API into working with a nuclear reactor that you might not otherwise have. And it was a very powerful system. And I want to finish up with very quickly with some lessons learned from this whole ordeal. And really, it's finding out what drives management, using those motivating factors to make that innovation happen, have a game plan, but most importantly, when you're dealing with new technology and new paradigms, is that you need to prototype early and often. The quickest way you can find out whether or not something is going to work for you is to prototype it. Get out there, get your hands dirty, build something that can take you onto the next level of your tech. That is the end of my presentation. Thank you so much. If you have questions, sorry, I think we have some time for questions, right? Perfect.
Yeah, we have 1 minute for a question. We went a little bit over time, but that was great. Again,
okay, thank you.
Extremely interesting. One question about, like, if you had to embed, because you talk about instruments, nuclear instruments. If you had to embed the software, like digital twins, we understood it's a parallel to the hardware, right? But
yes.
If you had to embed the software into instruments, would you still advise to use Rust for that?
It really depends on the instrumentation and the microcontrollers that you're dealing with. So if Rust can target it and can actually be compiled to work with that hardware, then absolutely. It is a very safe language. You're not going to run into nearly as many issues as you would be doing something in C++. But again, I mentioned earlier on that we have this idea of like ancient protocols that we have to deal with. In some cases, you might not have any other choice but to use an older language. But we are trying to move everything towards new modern languages whenever we potentially can. So
yeah, because at another conference, we got someone from NASA who told us, like, the most used programming language, or they still use Fortran or C, or
yes.
Because they say when we send something for 30 years in space, we need something that will be sure will be working for 30 years, right? So it has to be 30 years old. Yeah, So for nuclear, it seems you can go physically there at some point.
Yeah, and I think Rust is the programming language for the next 40 years. I think it's what we're going to send into space.
Okay.
To be honest.
Yeah, let's see. We will reinvite you in 10 or 20 years and ask for the prediction.
I appreciate it. Thank you so much.
Yeah, thank you very much, John. Extremely interesting. Thank you.